In a few minutes here, guys, just giving you the answers for worksheet number 2. You see 1 to 4 up there right now. I'll scroll down in just a second so you can see number 5. Or we'll flip the page, I should say, so you can see number 5. Finally, we'll take a look at 7 and 8 here. All right, you've had a chance to see the answers. What questions would you like to go over here today? I heard number 6 a second ago. 6 and 7. Any others? Okay, I got 3, 6, 7. 3, 6, 7, 8. Going once. Going twice. Okay, 3, 6, 7, and 8 it is. Question number 3 on your worksheet said, a 1,500 kilogram car accelerates from 55 kilometers per hour to 90 kilometers per hour. Calculate the impulse experienced by the car. The first thing that I spot when I read that question, before I even notice what's going on in the question, is just a couple of strange units, a couple of units that I don't like seeing. That's the kilometers per hour thing, the 55 kilometers per hour to the 90 kilometers per hour. So we want to convert both of those to meters per second. We got a mass here. We got a mass here of 15 kilograms, 1,500 kilograms, but we've got a VI of 55.0 kilometers per hour converted to meters per second, giving me 15.2777 meters per second. How did I do that, by the way? How did I find that initial velocity? Divided by 3.6. Good. And my VF is going to be 25 meters per second. Right? 90 kilometers per hour, 25 meters per second. Now, normally I say, take a look at the question, see what's going on before you write down your givens. Okay, notice I wrote down a couple of givens here kind of before I really looked at the big picture of the question this time. But I only did that because I noticed the kilometers per hour thing, and I didn't want to forget to convert it to meters per second. Okay, if I had the question up on the board right now, I just would have circled the kilometers per hour, and I would have worried about converting it later on. Okay. All we're looking for here is the impulse. So clearly it is an impulse question. Delta P is equal to F times delta T equals M times delta V. We do have one more given here before you actually write down that equation. It's 1,500 kilograms. Okay, we're looking for delta P, the impulse. Here's our impulse equation. Delta P is equal to F times T again equals M times delta V. We're going to use 2 parts of that equation. Which 2 parts are we going to use? 1, 2, and or 3? Which one? 2 and 3? I don't think so. Let's try 1 and 3. We're looking for the impulse, right? So let's circle the term impulse, change in momentum, and then let's circle M times delta V because we have M and VF minus VI. So it's 1,500 kilograms times VF minus VI. It's 25 meters per second minus 15.2777 meters per second. When we do the math there, we get 1.46 times 10 to the 4 Newton seconds. Anybody do that differently? Anybody say F is equal to M times A? Anybody use F is equal to MA? No? Okay. Is that a legitimate way to solve this problem? If you do it using F is equal to M times A, okay, and then actually, you don't have a time here, so I don't know that you could do it that way, actually. If you could, would you get the right answer? Yeah, it's a valid equation. Okay, F is equal to M times A is a valid equation when something accelerates. So you would get the right answer, absolutely. Okay. I'm glad that you did it this way because this is a really, really versatile method for solving a lot of problems, and that's what we want to be practicing right now. But in the end, on a test, if you do it some other way, you will get full marks. Okay, it doesn't matter how you do it as long as it's a legitimate method. Okay, the next one we needed to go over was question number 6, which says a 1.00 kilogram ball traveling towards a soccer player at a velocity of 5 meters per second rebounds off the soccer player's foot at a velocity of 8.5 meters per second. The time of contact is 0.02 seconds. What's the force that the foot applied on the ball? I know exactly where those of you who made a mistake on this one made the mistake. We have an impulse question here because we have a force and a time. Okay, delta P is equal to F times T equals M times delta V. And it's the same deal as it always is. But when we write down our givens here, okay, in all likelihood, lots of you made a mistake on the givens here. My mass here is going to be, for number 6, 1.00 kilograms. The soccer ball is traveling towards the player at 5.00 meters per second initially, before he kicks it. So VI is 5 meters per second. Okay, after he kicks it, it rebounds at 8.50 meters per second. The time was 2.00 times 10 to the negative 2 seconds. And we're looking for the force of impact here. I've made the mistake. I've made the mistake that I think a number of you probably made as well. What is it? I'm sorry? What is it? What is it then? No. No, it's not moving, right? Or sorry, it is moving, right? The ball is coming at 5 before this event takes place, and then after this event takes place, it's traveling at 8.5. What's the force of impact, okay, during this time that the speed changes from 5 to 8.5? Okay, now during that time, the ball does stop momentarily, right? Okay, but we're looking at the entire problem from start to finish, the impulse over the entire problem, and then for the force over the entire problem. What is it, Jackson? Something's got to be negative. Something's got to be negative. Okay, it doesn't matter whether it's the 5 or the 8.5 that's negative. Okay, let's say away from me is positive. If away from me is positive, then this will be negative 5. If towards me is positive, then the 8.5 will be negative, right? Something's got to be negative. Does that make sense? Okay, you messed up on that one, and you will get the wrong number, because when you go to subtract VF minus VI, you're going to get a different number. Let's say delta P is equal to F times T is equal to M times delta V. Which two parts do you want to use? The first part that doesn't appear on your data sheet, or 2, 3 that do appear on your data sheet? Which two parts? 2 and 3, sure. Okay, let's say F times delta T is equal to M times delta V. Let's rearrange that. It's a lot easier problem now that we recognize that one of those numbers had to be negative. M is 1.00 kilograms. Delta V is 8.5 minus negative 5. Or it could have been negative 8.5 minus positive 5. Either way. And delta T is 2.0 times 10 to the negative 2. It gives me a force here of 675 newtons. Or had you done it the other way, okay, had you defined away from you as negative, then what would the force have been? Would have been negative 675, right? If I'm defining, think about it. Which way am I kicking? I'm kicking away from me, right? So whatever direction that I defined away from me as, positive or negative, then the force must be in that direction. Okay, it must be. Bottom line is, the force has got to be in the same direction, the same sign as the final velocity. Because you're not going to kick it to the left and have it go to the right, or kick it backwards and have it go forwards. Number 7. Seven says a 1.5 kilogram rock falls from a 10-meter high building and strikes the ground. Calculate the impulse experienced by the rock during its fall. Well, this is a lot like the question we had on the quiz yesterday. It's also a lot like a number of questions that we've done in class so far, right? The only difference here is that we're not looking for the momentum as it hits the ground at the end of the problem. We're looking for the impulse during the fall, the change in momentum from start to finish. So this isn't really a two-stepper. Okay? Well, I shouldn't say that. It is kind of a two-step problem, but it's not really two problems. Okay? We're looking at the fall. That's it. Not the collision with the ground, but just the fall. As it falls down, it gains speed. As it falls down, it gains momentum. We know the mass of this thing is 1.50 kilograms. VI is 0 meters per second. It falls 10 meters, 10-meter high building, so we're going to say displacement is negative 10.0 meters. And we want to find the impulse Not as it strikes the ground, but the impulse during the fall. Let's say delta P is equal to F times T equals M times delta V. We've got part 1, we've got part 2, we've got part 3. Clearly, we're going to use part 1 because we're looking for impulse. Which other one do we want to use? Part 2 or part 3? 3? Who said that? Okay. I would probably go with that one as well. Okay. Although it is possible to use the second part, you're just going to have to do a little bit more work with it to find force, which would be gravity, right? And you'd have to find time as well. All right, delta P is equal to M, which is 1.5 times VF minus VI. We know what VI is, but we don't know what VF is. How are we going to find VF? Sorry? Yeah, do the same thing as we did for those other problems. VF squared is equal to VI squared plus 2AD. So it is 2 steps. We got to do 2 things to get this answer, but it's not a 2-problem question. We're not looking at this and then that. We're analyzing just the fall for the entire thing, okay? So square root of 2 times neg 9.81 times neg 10. That gives me 14.007, 14 meters per second. Now, technically, when we plug that in as VF, we're not going to plug it in as 14. We're going to plug it in as negative 14. Because we just found the final speed. This is the final velocity that we want. Do the math there. It works out to be negative 21.0. This time I said Newton seconds. Is that okay? Did anybody put kilograms meters per second for that? Is that okay? Yeah, they're both okay, right? They're both okay. Both mean the same thing. And number 8, a 1.5 kilogram rock falls from the top of a 10-meter high building and strikes the ground below. Sounds a lot like the last question. What is the force of the ground acting on the rock if it comes to a stop in 0.350 seconds? Here, this one's a little bit tougher, okay, because here we are looking at 2 problems. We're looking at the fall, right, as it falls, and we're looking at the collision with the ground. Okay, we weren't doing that in the last question. It was just the fall. Even though we had to do 2 equations, it was still analyzing just the fall. Here we're analyzing the fall, and we're analyzing the collision with the ground. We're looking for the force of the ground acting on the rock if it comes to a stop in 0.350 seconds. So it's going to be an impulse question, force and time in the same problem. Let's write down some givens here. For the fall, and then for the collision. We know that the mass is 1.50 kilograms for both the fall and the collision. The displacement during the fall is neg 10 meters, as it was in the last question. VI, let's say it falls from rest here. It's dropped. VI is 0 meters per second. It comes to a stop, so the collision lasts for 0.350 seconds. And I think that's all we have, isn't it? Looking for force here. What do you want to do? Listen, my habit when I'm solving a question like this, when I got to do a couple of different things, my habit is to write down the equation that I know I'm going to use first. Okay, I know I'm going to analyze the collision with the impulse equation. Right? I know that I am because I'm looking for force. I've got a time. The only way I'm going to get force here is to analyze it using the impulse equation. I know I'm going to use that part of the impulse equation. Anybody want to take a stab at which other part of the impulse equation I might use? Part 1 or part 3? Probably 3. Okay, we don't know that for sure until I go to actually solve it, but probably 3. Probably this one. That means F is equal to M times delta V over delta T. We know what M is. We don't know what VF is. We do know what T is. Okay, so I'm pretty sure it is going to be part 3 that I'm going to use here, but I've got to get VF. How are we going to do that? To analyze the... Oh, we did, didn't we? Yeah, using VF squared is equal to VI squared plus 3D. What was it? 0.00714 meters per second. So we plug that in as 14.00714. No, be very, very careful. Okay, VF is not 14.00714. VF is what? No. VF is 0, because we're looking for the force of impact of the ground on the ball or whatever it was that fell, right? So the force of impact causes the ball to stop. So during the fall, the final velocity is 14. But during the collision, the final velocity is 0. So we're going to say VF is 0. VI is negative 14.00714. You guys were right when you pointed out that it should be a negative. But it's not VF that's negative 14. It's VI that's negative 14. Does that make sense? It's moving negative 14 when the collision begins to happen. Now, in all likelihood, on a test, on a multiple choice test, they're going to ask you for the magnitude of the force, and you're going to get this right even if you made that little mistake that you guys just made. Okay? But just in case, we want to make sure that we understand why it should be 0 minus negative 14 instead of negative 14 minus 0. When we do the math on this one, by the way, I don't know if you guys noticed when I put up my answer key for that, I had a bunch of stuff scribbled out because I did exactly the same thing as you guys first. And then I caught myself on that one. When we solve that, we end up getting positive 60 newtons. Should that be a positive value? Mathematically, it works out to be positive, but should it be? Should the ground apply a force upward on the rock to stop the rock? Yes. Okay, so there's our little check, right? That's how I caught myself. When I solved this question and I got negative 60, I thought that doesn't make sense. You can't apply a force downward on a rock to stop a rock that's moving downwards. Matt? Yes, equal and opposite. Yes, absolutely. Okay, Matt just basically said, could we do it the other way and basically find the force of the rock on the ground? Okay, and then say, well, Newton's third law says for every action there's an equal and opposite reaction. The force of the ground on the rock must be equal and opposite, therefore positive. Yes, you could. Okay, if you go through that logic, that entire logic, then that would be absolutely fine. Yeah. We're good with all those questions? 100% on the quiz tomorrow? Lots of you have 100% in Physics 30. Week into Physics 30, 100%. Man, we have like a 90-something odd percent class average right now. Let's keep it that way, okay? Let's keep it that way for all of our quizzes and all of our tests and our diploma exam. Hey, listen, if you guys get a 95 average on the diploma exam, I'll probably have to do some explaining. They're going to think I cheated somehow. But you know what? I'd be happy to try to explain that one. Not sure how I would, but be happy to try. All right, let's spend a couple of minutes. Actually going over this question, question number 7. It's on page 11 or 12 of your multiple choice book. I'd like you to submit that, please, on your phones as multiple choice number 1, please. All right, let's take a look, everyone. 95% of us said the answer is C for this one, and 5% of us said the answer is A. So let's take a look at this and check to see if it's C. Let's hope it is. 95% of us are saying that. Foundation piles for tall buildings are hammered into the ground using a pile driver. A pile driver similar to the one shown below lifts a 900-kilogram hammer a distance of 3.5 meters above the top of a pile, then allows it to drop. You ever see that happening? You saw it here a year or two ago. You saw this a ton going in Deerfoot Trail at 22X where they were building all the bridges, right? They're driving these piles down to the ground. You ever wonder why they do that? Literally, as these piles go deeper and deeper into the ground, it's displacing more and more dirt. There becomes more and more of a force of the dirt pushing back on these piles, which creates more and more friction. What does that do? What does that do? It keeps them from sinking into the ground further, right? Because there's more friction on these piles. So in other words, it provides a good foundation for building something on top of. You want to build a bridge, drive these piles into the ground, literally, just drive them into the ground, and then build your bridge on top of it. You want to build a heavy building, drive these piles into the ground, and then build the building on top of it. If they're sitting on top of something that has so much friction on the sides acting on them, then they're not going to go down into the ground any further. And the building or the bridge or whatever it is isn't going to sink deeper into the ground. Does that make sense? And it's literally as simple as that. You see them, they lift up this hammer, they drop it. It goes down a couple inches. They lift up this hammer, they drop it. They keep doing that over and over and over again until these piles are down at ground level. Okay? So that's what's happening here. We want to find the magnitude of the impulse delivered by the hammer to the pile. So we're looking for impulse. Clearly it's going to be an impulse problem. Let's identify what's going on here now. This is going to be a two-stepper, okay, a two-problem. Okay? Two problems in one here, because we've got a fall. The hammer is falling, and then we're looking at the impulse delivered by the hammer to the pile. So we're looking at the collision. The fall, then the collision. We've seen a lot of problems like that, right, where we're looking at the fall and the collision. For the fall, we know the mass is 900 kilograms. For the fall, we know that VI is 0 meters per second. For the fall, we know that A is equal to negative 9.81 meters per second squared. And for the fall, we know that the displacement is negative 3.50 meters. During the collision, we know that VF is 0, right? Just like it was in that last question we did. As it hits and stops, the final velocity is, this hammer is going to be 0 meters per second. We want to find the impulse here. Okay, so for the second part of the problem, we're going to say delta P is equal to F times T equals M times delta V. Since we're looking for the impulse, okay, we're going to circle the first part of the equation and probably the last part, the third part. We know the mass is 900 kilograms. We know VF is 0 meters per second, but we've got to find VI. We've got to find VI here. Anybody make a suggestion as to how to find VI? It's not like we haven't done this before. But, yeah, it's the final velocity of the fall, right? So let's get VF squared, VI squared plus 2AD. Okay, this is 0, so VF becomes the square root of 2 times negative 9.81 times the displacement of negative 3.5. So whatever we get there for the final speed, okay, that becomes the initial speed of the collision. But we're going to make it a negative value there because it's downwards. Okay, solve for the impulse there, and we do, in fact, get C, 7.46. That's actually 7.46 times 10 to the 3, but notice they have a kilo in front of that, right? So that's still correct, 7.46 kilonewton seconds. Is that good? Okay, I don't want to do this question here. I just want to real quickly address it here. How would we look at question number 8? How would we analyze that one? The impulse is delivered by the pile driver in 2.1 times 10 to the negative 3 seconds. What's the force? What have we just solved for, Tanner? Right? We want to find force. We've got time. All we do is delta P is equal to F times T, right? Is that good? All right, real quickly here now, just so that we can cover one more thing before we drop our eggs in about 15 minutes. I want to review this qualitative impulse thing. We had two situations that we described by impulse, right? What were they? Stopping and starting, or predetermined and non-predetermined. Okay, they both mean pretty much the same thing. When you're stopping an object, the impulse will be predetermined. You're not going to control the impulse. The impulse experienced by the car traveling down the highway when it comes to a stop is simply dependent upon how heavy the car is and how fast the car was moving. It does not depend whatsoever on how the car comes to a stop, whether it crashes into a wall or whether it comes to a gradual stop at a stoplight. Okay, the impulse experienced by you as you jump off your desk is predetermined. Okay, it's determined by how fast you were moving when you hit the ground and your mass. Simple as that. When you have a predetermined impulse, the impulse will not change. The impulse will be the same no matter what. Typically, the goal when you have a predetermined impulse is to increase the amount of time that it takes to stop. Bend your knees, takes longer to stop. Use an airbag, takes your head longer to stop. Use a baseball glove instead of your bare hand, takes longer to stop. Okay? Put your foot on the brake versus crashing into a wall. Okay, it takes longer to stop. When you increase the stopping time, that does what to the force? Decreases the force. Okay, and that's really what we're looking at there, right? Is decreasing the force. We don't really care what the impulse is. Okay, think about it. Hey, most of you guys have probably flown on an airplane before. Airplanes weigh how many thousands of kilograms? Okay, you got 125 people on there that each weigh probably on average 150 pounds, 70 kilograms. It's massive. It's absolutely massive. And it's traveling at, say, 900 kilometers per hour. That's a ton of momentum. That airplane will experience a whole lot of impulse, no matter what, no matter how it comes to a stop. But you know that it's safe as long as you come to a fairly gradual stop on the runway versus a very quick stop by just slamming into the ground. It doesn't matter what the impulse is. What matters is what the force is. Okay, when you come to a gradual stop on the runway, the force is smaller than if you come to a really quick stop when you crash into the ground. Second aspect, the second implication of qualitative impulse is this whole non-predetermined impulse. This is when we're starting something. This is when we're starting an object. Maybe we're hitting a golf ball off the tee. Maybe we're taking a slap shot with a hockey stick. Maybe we're throwing a baseball. Okay, maybe we're hitting a baseball with a bat. In the end, when we have a non-predetermined impulse, we're trying to give it as much impulse as possible. Okay, we do that in two ways. If we increase the time, it doesn't decrease the force. If we increase the time, it increases the impulse. Similarly, if we hit it harder, if we increase the force, it will also increase the impulse. Okay, does that make sense why we have increasing time, decrease force up here, but yet when we increase the time, we don't decrease the force here? It's not a predetermined impulse. That's why. All right? The only thing that I want to do new today with you is finish up impulse, basically, and that's going to just require us to take a look at F versus T graphs. Force versus time graphs. We'll see these fairly often. A force versus time graph is going to always have force on the y-axis and time on the x-axis. Sometimes it may be something as simple as this. Sometimes it may be like this. Sometimes it may even go below the x-axis and look something like this. Whenever you see that graph, I don't care what you're asked. I don't care what the question says. I don't even care if you read the question right away. When you see that graph, I want you to think three words. Area equals impulse. I don't care what the question asks. I want you to think area equals impulse. And then I want you to calculate the area. And you can do that, once again, before you even see what you're being asked to find. Before you even read the question. You know you're going to do that. Now, how would we find the area of this graph? Well, because it's kind of an odd shape, we'd have to break it up into sections, right? The area 1, which would be 1/2 base times height because it would be a triangle. Area 2, base times height is a rectangle. Area 3, 1/2 base times height because it's a triangle. And area 4 down here because it's a triangle. Always find the area between the x-axis and the line. If it's above the x-axis, it's going to be a positive value. If it's below the x-axis, this one would be negative. When you find the area, you've found the impulse. Done. Okay, the area equals the impulse. Now, every once in a while, the question may go a step further and say, what's the change in velocity? Well, once you get the area, you've got the impulse. If you're given the mass, and you've just found the impulse, then you could find the change in velocity pretty easily, right? Or alternatively, if you were given delta V and you wanted to find mass, you could do that fairly easily as well using the m times delta V equation. The equation that you don't want to use here is this one. Anybody suggest maybe why I don't want to use delta P is equal to F times T? Yep. Yeah, kind of. We'll come back to that in a second. Yep. Yeah, it's triangles. In other words, force is changing. Right? What value of force do we use if we want to use this equation, right? The force is always changing there. It's triangles. Okay? It's different shapes. F times T assumes either constant or average force. If you could find the average force here, then you could use that. But that's a challenge to find the average force there. The only time you ever want to use that equation for an F versus T graph is if the graph looked like this, if it was a constant force. And then really all you're doing there is finding the area. So you might as well just go back to area equals impulse. Okay, let's take a look at one example, guys. Just one. And then we'll drop our eggs. A golfer hits a long drive, sending 45. Hey, even before I read this question, I see a graph. I see an F versus T graph. What do I think? 3 words. Area equals impulse. I know that area is going to equal to impulse. Maybe even write it down. A golfer hits a long drive, sending a 45.9 gram ball. Circle that gram because it's in non-standard units. Net force is a function of time. What's the impulse provided to the ball? What's the velocity of the ball the moment the ball and the golf club have separated? To find A, I'm just going to do the area. And since it's a triangle, we're just going to say 1/2 base times height. The base here goes from 0.1 to 1.1. So the base is going to be 1.0, right? 1.1 minus 0.1. And the height is 5,000. Oh, wait a second. I almost made a mistake here. You notice this? Those are non-standard units as well, and I missed those when I looked at the question. Millisecond is 10 to the minus 3. So my base isn't 1. My base is 1 times 10 to the minus 3. 1 millisecond. The height's still 5,000. I think when we do this, it works out to be 2.5 Newton seconds. Impulse, 2.5 Newton seconds. Now, if I want to find the velocity of the ball at the moment the golf club and ball separate, let's say impulse is equal to m times delta v. Delta p is 2.5. Hey, when does the ball and the club separate here? Is it who votes for position A versus position B? When do the ball and the club separate, A or B? Who says A? Who says B? Of the people that voted, it seems to be about 50 and 50. The answer is B. They separate at B. Look at it. The force is getting smaller here, but it's still not 0. You cannot apply a force of the club on the ball if the club and the ball aren't touching each other. So they have to be in contact here. Where do they leave contact? When the force becomes 0. Now it decreases. And it's decreasing because you know that as the club flexes, okay, it reaches a maximum flex, applies a maximum force, but as it starts going back to being straight, closer to being straight, okay, then it's going to reduce the force that it's applying on it. So it does become a smaller force as you follow through, but it's still a force and it's still in contact. So we're going to use that entire impulse divided by the mass of 0.0459 or 45.9 times 10 to the minus 3. And when we do that math, we should get 54.5 meters per second. Does that make sense? Okay, so only one new thing today. Okay, we also reviewed Beyond this graphing stuff that was new, we also took a look at the qualitative implications of impulse, just as a review. Neither one of those will be on your quiz tomorrow, just the mathematics of impulse. This stuff, first of the week, next week, will be on a quiz. You do have a little bit of homework. It's only 2 questions, though. Sorry, 3 questions. 3 questions. Page 462, number 1 and 2. And what else? The last question on the worksheet. Worksheet number 2. Question number 9.